Hello, everyone. I cannot say good morning. It's 6 minutes past 12. So good afternoon, everyone, and welcome. Greetings also to all of our Zoom attendees, and thank you for joining us. I'm George Deodatis, the Vice Dean for Research of Columbia School of Engineering and Applied Science and professor in the departments of Civil Engineering and Engineering Mechanics and Earth and Environmental Engineering. I'm pleased to be here with my fellow panelists, Candace Agonafir from the Columbia Water Center, Fatoumata Camara from Barnard College, and Adam Nayak from Earth and Environmental Engineering, as well as today's facilitator, Savannah Thais from the Data Science Institute. As you can see, we have voices from across Columbia University, all joined by the work of LEAP, and National Science Foundation Science and Technology Center, launched in 2021 and led by Professor Pierre Gentin of Columbia School of Engineering and Applied Science. From the very beginning, LEAP has been focused on collaboration. It is a consortium of universities working with leading climate research labs and computing-related organizations. This type of sharing and collaboration is essential to the mission of LEAP and to advancing the center's goal of improving climate projections through the latest advancements in climate research and data science. So today we have the opportunity to delve into an interactive discussion on climate modeling with a focus on flood risk, a risk that is increasing as floods become more frequent and more intense. Some important related questions include: how can better climate models help us address this issue? And how can we use this information to help communities at risk? That is what we are here today to discuss and to answer any of your questions. I would like to mention that here in New York City, it is Climate Week, and Columbia Engineering has a full set of events in support of this week to draw attention to the great work being done at Columbia on climate action. So please check our website if you are interested in learning about more events. So I'm very excited to have the discussion that will follow the presentations, and thank you again for being here, and thank you, Savannah, for leading this discussion. I believe we have the agenda, the names, the presenters, the one acknowledgement. I will leave it for a minute. If you want to learn more about what will it take to electrify the energy system, you can scan the code here. I'm sure this will be available to everyone. Also, if you are far away, to scan. I will go directly to my presentation. So I'm going to talk today about the combined effects of coastal storms and sea level rise on New York City's infrastructures, and I will focus on optimal adaptation and resilience strategies. This is the research group that has worked on this topic, and it includes colleagues of mine from the School of Engineering, PhD students, master students, and undergraduate students. So these are 4 photographs of New York City before the 2012 Hurricane Sandy. And these are the same locations after Hurricane Sandy. As we know, a lot of flooding, fire following the flooding, blackouts, and so on. Overall, $65 billion in damage. Out of this, $19 billion in New York City. Unfortunately, very heavy loss of life, 233 deaths, more than 5 million people without power in the northeastern United States. And this is a table of the costliest hurricanes in US history, and these numbers are adjusted for inflation. So you see that out of the top 6, 4 have occurred post 2017. One of the drivers of this increase in big hurricanes and losses is, of course, sea level rise. As you can see here, this is sea level rise in New York City up to this point, measurements, and these are the projections with a high, a low, and the mid estimate. And these are projections done by scientists at Columbia University. Now, let me go back a little bit. This is a study that we conducted a year before Hurricane Sandy. This is Lower Manhattan. This is Lower Manhattan, Brooklyn, and our projections for flooding of the tunnels, thick blue lines means flooded tunnels. We made a presentation to the MTA. They said, we believe you, but we don't have any money to do anything. And then Hurricane Sandy occurs, and we have this devastating outcomes. And you might say, okay, this is unique to New York City. New York City did not act preemptively. I would beg to differ. This is a universal problem. And people might think, okay, the Netherlands, well, they have done everything before disasters struck. The facts are a little bit different. This is Cornelius Lely on the left. He tried, a civil engineer, he tried very hard to convince the Dutch parliament to take action to protect the northern part of the Netherlands. He was disregarded. He became a politician, entered politics, was elected to the Dutch parliament, became Minister of Public Works. Still, he was not able to convince the Dutch government. And then a major flood in 1916 occurs and leads to the implementation of Lely's plan. And you might say, okay, they learned their lesson. The answer is no. Johan van Veen, personally selected by Lely, who has become a national hero by that time, to devise a plan for the southern part of the country that had an even larger problem. Again, this plan is disregarded until there is a major flood in 1953 that leads to the implementation of Van Veen's plan. So this is universal. It's not New York City that has not acted. Pretty much no one is acting beforehand. I'm not blaming the politicians. The politicians have other priorities: healthcare, education, spending significant amount of funds for something that's going to happen in the future is not that easy. So today we are 12 years after Hurricane Sandy, and the New York City metropolitan area is preparing for a repeat, essentially, of Hurricane Sandy. This is not the best approach. Among other reasons, the next catastrophic hurricane in the city is not going to have the exact same flooding inundation patterns like Hurricane Sandy. An example, this is the flooding that occurred during Hurricane Sandy. Manhattan, Brooklyn, the blue color shows the areas that flooded. But Sandy occurred at high tide in this part of the city. If Sandy had occurred at low tide, That would have been the inundation pattern, much, much less. Keep in mind, high tide to low tide in New York City is around 2 meters. Very significant. Accounting, storm surge of Sandy was 2.7 meters. Now, the northern part of New York City, this is the upper part of Manhattan, the Bronx and so on, dark blue, forget about this, LaGuardia did not flood. Dark blue are the areas that flooded during Hurricane Sandy, but this part of the city was at low tide. If it were at high tide, the light blue areas would have flooded. Very little, if anything, is being done right now in this part of the city. So what we need is a general framework to determine, for a given budget, optimal adaptation and resilience strategies to protect everyone, population, infrastructure in coastal areas. Now, to do this, the only way is to follow a probabilistic approach because there is so much uncertainty as far as the hazard is concerned, future sea level rise, the tidal cycle, and so on. And the optimal strategy is not going to be one solution. Let's build a wall all around us. No, this is not the optimal approach. It's going to be most probably a number of different protective measures implemented at different geographical locations and at different times. And of course, stakeholder feedback, equity, social justice, and social acceptability are critical. And we are considering them because you might come up with a solution. This is the best way. Build a 20-foot wall in front of you. Community is going to come and say, we don't want this out of the way. So social acceptability, very, very important. Okay, first we have to quantify the hazard. Probabilistically, we can use either data or simulations. And these are last 100 years of data at the Battery in New York City, storm surges of storms. Blue are cold season, red are warm season. This is Hurricane Sandy here. Using the data, we can find probabilistic models to make it easy to understand. This is the storm intensity in terms of return periods. Warm season, this is Hurricane Sandy here. It's around between 200 and 300 years of return period. There's a big unanswered question. How are storm occurrence and storm intensity models going to change in time because of climate change? They're going to change. We don't know exactly how. There's no consensus. When consensus is going to build, it's very easy to introduce them to our model. These are Columbia University estimates about New York City sea level rise projections between now and the end of the century. As you see, for the end of the century, it's a very wide range from 40 centimeters to almost 2 meters. These are periodically updated, and they always go up. I have never seen them go down or remain the same. What can we do? So many different approaches, nature-based protective measures, restoration of wetlands, restoration of sandy beaches, sand dunes, and so on. Engineered measures, seawalls, barriers, elevating the infrastructure, sealing the infrastructure, but there are other measures also. Managed retreat. Some communities might have to move. Or we can use insurance, reinsurance, catastrophe bonds, resilience bonds. This is the methodology to find the optimal protective strategy. It's an optimization methodology. And I want to emphasize that different budgets will lead to different optimal strategies. Of course, if you have more money, you can do more. But for every given budget, we can determine the optimal adaptation strategy. We take into account stakeholder feedback and social acceptability. And these are all the agencies that we have communicated with in New York City, including affected communities. We went directly and talked with the communities, as well as a lot of different agencies in New York. And just a couple of slides. This is a very, very preliminary example. Here we are considering only one protective measure in Lower Manhattan, essentially a combination of an elevated promenade and the seawall. This is known as the Big U. And what we're going to try to optimize here in which locations to build it, at what height, for a given budget. So in the horizontal axis, you see different budgets. So for a budget of $500 million, it's the best way to protect this area. Build a wall or an elevated promenade, which is probably possible in this part, from here to here at a height of 2 meters. And we'll spend the $500 million that we have, and this is going to give the maximum protection. If the budget goes up to $1 billion, as you see, the length of the wall is extended again 2 meters high. And if we go to $2 billion here, we can cover the entire perimeter with a wall of 2.5 meters. This is not going to prevent damage completely, because we are expecting events with a height above 2.5 meters. But this is going to give the maximum protection. I'm going to stop here. Just wanted to say that now we're extending the methodology to include multiple protective measures, not only elevated promenades and seawalls, but restoration of wetlands and sealing individual components of the infrastructure. Of course, not in Lower Manhattan. We cannot restore wetlands in Lower Manhattan, but in other parts of New York City. Thank you very much.
Hi, so I'm Candace Agonafir, and a little of what I'm presenting today is in my review of urban flooding. It's called a review of recent advances in urban flood modeling and mitigation techniques. So basically, due to a changing climate and increases in urbanization, we're seeing an escalation of urban flooding. And the after effects are more severe. Notably, the frequency of extreme storms is expected to rise. And as we are having more built environments, we're going to see the absorption of water being impeded. And so we're going to have the threat of devastations, especially the threat to human life and to financial, if to finance or economic damage will occur. So the review is going to detail the concepts, the impacts, and causes of urban flooding, along with associated modeling endeavors to identify risk zones and the engineering techniques employed to reduce the runoff. So let's begin by talking about the types of flooding. So we heard about coastal flooding, and that is a reality in New York City. Coastal flooding is defined by inundation of water onto land by nearby coastal lands. It can be caused by heavy rainfall, high tides, or onshore winds. We also have riverine flooding in the United States, also in New York City. Riverine flooding tends to happen in middle America more. Coastal flooding happens at the coast. But basically that is when water submerges the land by high tide or increased water levels of the river. We have pluvial flooding, and that's the type of definition that mainly applies to urban flooding. It's independent of a large body of water, and a lot of times the urban drainage system has an effect. So basically the water, it cannot go into the ground, and so the drainage system, the underground sewer system is important. And then we have flash flooding, which is also important to the urban system. So that's flooding that begins within 3 to 6 hours after a sudden onslaught of rain or another cause such as the breach of a dam. Now, urban flooding is propagated by the specific characteristics of urbanization, and the urban landscape plays a contributing factor. So let's talk about the effects of urban flooding. First, we have death. That's a regrettable outcome, but it is possible during flooding events. There's not extensive literature on the deaths directly related to urban flooding, but if we look at the aftermath of post-tropical depression Ida, we saw 44 deaths in the New York City metropolitan area, and that includes Westchester, New Jersey, and New York City. We saw 13 deaths in the New York City area. Most of it occurred in Queens, and they were a result of basement flooding. So people who were trapped in the basement during the flooding time, they couldn't get out. But overall in the United States, we have around 100 flood-related deaths annually, and we have close to 5,000 deaths internationally per year. So it's not just the deaths that could occur that is a human consequence of flooding. We also have water contamination, we have injuries, animal bites, puncture wounds. It's just a dangerous situation when an area is being flooded. So when we think about the economic damage, it can range from an event causing billions of dollars of damage, and Hurricane Ida is an example of that. The incident resulted in greater than $75 billion of damage overall to the US. But there's also indirect long-term costs as a result of flooding. So these costs can be destruction to the infrastructure, slow erosions, where equipment might have to be replaced. But you also have secondary costs. This can be to Uber drivers, for instance. Maybe they can't drive because their car got flooded. I think I was in an Uber in May or at some point in Westchester, and he came in the wrong car. So I guess I asked him, what happened to your car, right? And he said it was flooded. So I guess, which I don't think they're allowed to do, but still, you can see how that might have an effect. So people who are salaried, right? So they can't go to work that day, the subway's not running, then that costs them money, it costs their family money. And also the replacement of vehicles. So as I said, urbanization is a cause of urban flooding, obviously. The urban environment is not of aid to rainwater infiltrating the ground, right? You can't infiltrate concrete. So urbanization is a cause, and that's expected to increase in the US and globally. Climate change is a cause of urban flooding. You're going to see warmer water surface temperatures. That's going to result in intense rainstorms, more hurricanes. For instance, for every 1.8 degree Fahrenheit increase, we are expected to see extreme storms increase by 21%. The greater rainfall amounts or intensity, they're going to exhaust the current drainage system. So the drains are created at a certain capacity, and if intense rainstorms increase, then you're going to need a larger drain, right? Because the water's coming more, and if you can't drain it out, it's going to stay on the floor, right? Or you might get extended surcharge. So the water is actually coming from the drain onto the ground. So that's even worst case scenario. So yeah, the factors that are known to aggregate urban flooding. So if you're going to model urban flooding, you need to know the variables involved. So precipitation obviously is a variable that causes urban flooding. You can look at total daily rainfall amount. You can look at the storm duration. You can look at storm direction. But these are all related to the precipitation variable. Topography has an effect on urban flooding. Higher elevations and steeper slopes, they reduce flood risk. So if you're at the bottom of a slope, then you have a higher chance of flooding. You have land features, which we talked about, the impervious ground surfaces, asphalt, concrete, buildings, increased flood risk. You have infrastructure issues. So urban flooding is in an urban area, so infrastructure is very important. You can have catch basin issues. Catch basins are the mechanism for which the water goes into the sewer network. So if the catch basin is blocked, then the rainwater cannot enter, and therefore it's on the street. You have sea level rise. This induces coastal overflow during rain events. This will increase. So that's an issue for the Rockaways, Coney Island, when we're looking at New York City. So what can we do as researchers to alleviate the situation? We can create models. Models allow us to forecast when flooding will occur, or allows us to identify a risk zone. So it gives us a chance to perform preventative measures. We have the hydrologic modeling that's very popular. It's what it does is simulates the water path. It can simulate the drainage system, and then you can kind of get an idea of where the water is going to flow, where it's going to flood, just based off of the drainage capacity, et cetera. But in New York City, researchers don't have access to the hydrologic drainage network. So we don't have access to the drainage network. And so we can't really perform these physics-based models. But the advantages are that they have accurate risk assessment and prediction. And the disadvantages are that they require that drainage data that we don't have in New York. They have long computational time and they have high costs. So what can we use in the meantime? We could use statistical models. We could use machine learning models. A very popular method is the employment of regression-based models. So you can use a generalized linear regression model, perhaps look at the variables, and then see which predictors have the greatest effect of flooding. You can look at, or you could use machine learning, which is trending in flood literature recently. So you can see the green line here is showing how artificial neural networks have trended in in flooding literature since 2008 to 2017. But other machine learning methods have trended, especially decision trees like random forest, CART. So machine learning, it reads the environment, it learns, and then it provides useful information. Artificial neural networks and decision trees are the most popular right now. They give the most robust results. But engineers can do things as well, and people in the community can support these endeavors. They can employ mitigation techniques. So we have an area called low impact developments. These are engineered designs to improve infiltration in urban areas. Green roofs, you might have heard, are very popular, and actually New York has mandates in regards to green roofs. You either have to install a green roof or a solar panel if you have a new retrofit to your building or to the roof. We have permeable pavements. They absorb rainfall and slowly release it. And then we have rain gardens. They sit at the bottom of an incline. They infiltrate runoff. So there's some engineered designs, and that's something the community can get behind and support. But to end this review, basically, what do we need to know about urban flooding? It's very dangerous. Fatalities can result. We already lost people in this own city of New York. You could have injuries. There are large-scale direct economic damages. There are also indirect economic damages. We're going to experience extreme storms due to climate change and urbanization. So we need to prepare for that. We can employ models as researchers. We can use physics-based models. But if we don't have the necessary information, we could be creative and use AI or data-driven statistical techniques. And that's the end.
Hi, my name is Fatoumata Camara. My project is visualizing flood impacts in New York City neighborhoods due to climate change, and my mentors are Dr. Tian Zhang and Dr. Candace Agonafir. Okay, so a little bit about me. My name is Fatoumata. I'm currently a senior at Barnard College studying computer science with a minor in environmental science, and I'm also in the program SV Squared, which stands for Science Pathway Scholars Program, and is for underrepresented groups in the sciences. So to get a bit into it, we like to say that privilege is both a cause and result. To understand climate justice, it's imperative that we examine the impacts of extreme weather along with the multiple directions to paint a more holistic picture. So with this, flooding in New York City has become an increasingly significant issue with factors including climate change, geographical features, and urban development impacting it. With this, in September of 2022, the U.S. Army Corps released a $52 billion storm surge proposal that would protect New York City metro area against storm surges and coastal flooding. The barriers they were designed to protect New York City against flooding and damages against storms like Superstorm Sandy, which occurred in the region in 2012. So to get a bit into the proposal, as outlined, they have three methods of protecting New York City. There would be one primary storm surge barrier, risk reduction features, and induced flooding features. Induced flooding features would include nature-based methods that would offset the impacts of increased water levels due to the presence of a storm surge barrier. And the goal of this would be to reduce the induced flooding that would occur. And risk reduction features would be intended to be placed in areas considered to be the most vulnerable, as stated by the U.S. Army Corps. And these would be inland or water-based measures. And this would protect areas against coastal flooding and from the closure of a storm surge barrier. And these measures were set to be quickly implemented to protect areas considered to be the most vulnerable. And in this map, you could see where the primary storm surge barrier was set to be put in place. These are where the induced flooding features are set to be put in place and the risk reduction features. The risk reduction features are all placed in Manhattan, Brooklyn, Queens, Staten Island, and parts of New Jersey, while induced flooding features are all put in the Bronx. Okay. So from evaluating this, we wanted to see whether risk reduction features were truly being placed in areas that were considered to be most vulnerable. Locations identified to have risk reduction features were said to have an elevation plane of 7 feet or below, as stated by the North American vertical data. So as New York City flooding is becoming an increasingly significant issue, it's imperative that we identify accurately which areas are actually most vulnerable. And our hypothesis is that the Bronx does experience flooding to a similar extent to other areas in New York City, and it should also have risk reduction features placed there as well. So to understand this, we did a lot of data collection. We collected data from NYC Open Data 311 reports from the years of 2010 to 2024. And we collected data specifically for street flooding, highway flooding, and general flooding. And this was during specifically major hurricane events or major flooding events. And along with this, we collected census data for housing information and demographic data. And we also collected FEMA data from the National Risk Index, which would indicate whether an area is at risk for, say, coastal flooding or riverine flooding. And this is an example of what an ArcGIS attribute table would look like after inputting all the data and combining the data sets together. So this has demographic data, location data, as well as flood complaints. And along with like zip codes, so then I would be able to actually map it along with location data, but that's like further within it. And the NRI is also within it. It's a very big data set. Okay, so going into the results, we can see that I mapped the flood complaints. So by size, we can see whether an area is actually producing flood complaints. So if an area has a bigger circle in red, then that means that they are complaining more. And by color, if an area is more pink, then that means that it is more at risk for a certain thing. And if it is more blue, then that means it has a higher building value. So in this case, the Bronx and Staten Island have a low expected total loss in case of hurricane with a low building value, while Manhattan and Queens have a moderate expected total loss in case of hurricane with a high building value. And Brooklyn is high in both regards. In the next one, we can see that the Bronx has a moderate expected total loss in the case of coastal flooding with a low building value, while Manhattan has a moderate expected total loss in the case of coastal flooding with a high building value. Brooklyn is high in both regards, Queens is moderate in both regards, and Staten Island is fairly low in both regards. Lastly, we can see riverine flooding. The Bronx is moderate with the expected total loss in this case with a low building value. Manhattan and Queens have both expected total loss in this case with a high building value. Brooklyn is high in both regards, and Staten Island is expected to have a high total loss in this case with a low building value. So from this, we can see that although the Bronx has a low expected total loss in the case of hurricanes, it does have a moderate expected total loss in the case of coastal flooding and riverine flooding or ravine flooding. So it should be protected within this, or it should be considered to be as most vulnerable, since in comparison to Manhattan, they also have a low expected total loss in the case of riverine flooding, I believe, but a moderate expected total loss in the other two cases. So, but the only difference with the two is that Bronx has a low building value and Manhattan has a high building value. And later, I would like to add the topography onto the map so it's more visually representative, so we can understand which areas actually have a floodplain of 7 feet or below, so that we can compare to see if the Bronx actually should be considered in what they say is protected. But this map also shows the elevation of New York City, and with color, you can see that the Bronx does share some topography similar to other areas in New York City. So with our current findings, there should be no reason as to why the risk reduction features are being placed in the Bronx as well. So our next steps, as I said, would be to add the topography to the map so it's more visually representative, and conduct more geoprocessing to allow for data set consistency. And I would like to continue working on a website so individuals can access this data, so they can actually visualize and interact with the maps to gain further knowledge at this issue at hand. And these are my references, and thank you.
Hi, everybody. My name is Adam. I'm a second-year PhD student. I work with Professor Gentine and Professor Lal in the Department of Earth and Environmental Engineering. And today I'm going to share with you kind of a general overview of what we have been working on, specifically on learning socio-hydraulic compound flood risk. So what is compound flood risk? That's not necessarily a term that a lot of people generally use to describe flooding, but it's actually really important, largely because in general, floods tend to cluster in both space and time. So if we think about like a storm, it's going to move over a certain trajectory, and likely in that trajectory, you're going to have multiple occurrences of flooding that are spatially correlated. And then you also potentially in a year that is higher risk, or you have climatic drivers that are driving multiple occurrences of storms in a shorter period, you might have repeated floods along these same trajectories. So you can think of instances such as maybe atmospheric rivers in the news, where you have multiple floods occurring in places like California in a short period of time. And these effects can be largely detrimental because you have this sort of repeated risk and repeated impact. And so these long duration and clustered extreme events tend to have larger socioeconomic impacts as well, which can be very detrimental, specifically for communities that are ill-prepared for these storms. And under climate change, we project more frequent and intense rainfall. Now, with that, we have to consider that we also have increased pressures on infrastructural strain and increased pressures on population growth in flood risk-prone areas. So these things lead to these compound stresses that we really want to be focusing on as we as planners and engineers are trying to mitigate these hazards. So at the same time, we have natural human barriers. So in order to have effective adaptive planning strategies, we need to think specifically about communities and their willingness to adopt infrastructure, adopt insurance, and adopt preparedness mechanisms like Professor Deodatis mentioned earlier. And these engineering solutions often rely too heavily on the fact that we maybe are adopting rational decision-making processes and will neglect socio-cultural factors in human decisions and trade-offs. So we need a larger centering of holistic solutions that will consider these adaptive interventions within the larger socio-hydrologic system, meaning we need to think about our human structures as well as the natural drivers and think about critical intervention points that react to the human system, but think about the risk that the natural driver might pose. So what we're really working on is this sort of cascading dynamic approach to infrastructure and financial planning with a specific focus in resilience measures. So we want to be thinking about climatic non-stationarities, such as climate change, such as El Nino, but we also want to be thinking about regime drivers. Areas in the country have different regimes that are going to be driving the flooding, whether that's snowmelt patterns, whether that's atmospheric rivers, whether that's hurricanes. And we want to be thinking about solutions that meet these drivers where they are at, what's actually causing the flooding in this given region. And we also want to be thinking about the response. We have to think about the ways in which our emissions pathway may inform the way in which we're modeling things like sea level rise. We also want to be thinking about the financial markets and our infrastructure in terms of proactive investments that meet the risk where it's at within who's actually being affected, who's actually frequently experiencing losses. And so our project specifically focuses on integrating elements of game theory, stochastic modeling, and machine learning to examine the natural human system in a way that we are There you go. We're looking at ways in which we can examine these sort of behavioral drivers and the system failure points within the natural human system. So we have like a multi-step approach to examining this. So first, we want to examine the ways in which we are simulating these sort of compound flood risks. We also want to examine the behavioral drivers. And then finally, we want to learn the sort of cascading adaptive pathways that can best prepare us for the future. So in our first application, we are really looking at this sort of way to simulate compound flood risks in a way that considers the spatial and temporal clustering of hydroclimatic extremes. So we use a multi-step process in which we first derive a hydroclimatic signal from historical data on a year-to-year basis. We then use that signal to forecast future potential trends in how hydroclimatic extremes may respond over time, considering climate change and considering oscillatory behavior. And then after that, we simulate future compound events and clusters of storms conditioned on that given climate year. And how we do this is we basically look at the projected signal. We then look at the historical record of the nearest instances or the nearest neighbors of this signal. And then we use that data of clustered events to then simulate future scenarios. So we parameterize or design our model for clustering based on a conditioned signal for a future climate. So we evaluate this model in 3 different river basins in the United States. These are along 3 of the major river basins in the US. So the Mississippi River Basin, Clark Fork is a tributary of the Columbia River Basin, and the American River is in California. We wanted to represent a wide variety of different hydroclimatic regimes in this area. So we wanted, a dry region. We wanted to look at the Mississippi, and we wanted to look at the Columbia. And largely speaking, our simulation is able to replicate a large range of historic hydroclimatic conditions, but then it also is able to demonstrate its an ability to go beyond or basically simulate future scenarios that aren't necessarily reflected exactly in the historic record, which is really important as we consider things like climate change in the future. So the model foregrounds the important role of physics-driven compound risk modeling and specifically for strategic adaptation planning. And so from here, another piece of work that we're focusing on specifically is trying to tease out some of these more like behavioral drivers, who's being affected by flood risk and how can we best intervene to meet these communities where they're at. And game theory provides a pretty great framework for this to a certain extent, because in games, we kind of are looking to specifically evaluate cooperation and conflict. And within our systems, cooperation and conflict are inherent in any of these decision planning scenarios. And so if we look specifically at using different game theoretic frameworks, we can actually find new insights. So here's an example of one of our games. And this is a pretty simple cooperative pool game. So if you think about flood insurance, as insurance is kind of like a money pool, right? You have people pay an annual fee, and then if you incur a disaster or you have a loss, you withdraw from that pool. And so you can kind of think of it as, your value add to the system, which is the common pool of insurance, is how much you pay minus the expected amount that you might withdraw. And so we can evaluate this not only on the state level, but also at the county level based upon historic flood records through FEMA. FEMA holds the National Flood Insurance Program. Flood insurance is 95% covered federally, so it's covered in a public pool. That's largely because insurers withdrew from the private market in the 1900s. And so now the federal market is like basically a monopolistic market here in the US, which also has insights for things like homeowners insurance, where folks are withdrawing from that market today. And what we see here, which is very interesting, is if you look at just the current risk-based premiums, which FEMA has updated annually, and then we take the expected claims by county, and then look at their net contribution, of course, adjusted for inflation, the areas that are negative or in the pink below aren't necessarily where you would think, oh, this is the highest risk area. And part of that is actually because in areas such as Florida or Houston, Texas, folks have a much higher uptake of insurance, and they also are frequently paying higher premiums versus in some of these regions that are more rural or potentially have lower population density, but still exhibit risk. They are paying less, but withdrawing a greater sum of money. So their expectation of their claim ends up being higher. If we look specifically at the counties who are at an expected loss, what we actually find is on average, there's higher rates of poverty in these counties, lower household income, and also we see that they're almost predominantly rural. So most of the counties that are exhibiting losses tend to be in rural areas or suburban areas and exhibit a higher loss per claim per year than areas that are in large metropolitan areas, which is also in some ways a little bit counterintuitive because a lot of our focus in floods sometimes is in urban flooding. So then if we even go a little further and look at the federal dollars that we allocate towards mitigation efforts, we actually see another issue of equity, which is that we have for interventions for mitigation projects, so investing in infrastructure such as a home elevation, such as floodproofing versus buyouts or planned relocations or managed retreat. These are all within the same realm, basically buying someone's property out because they incurred so much damage to their after a flood. We see a significantly higher instances of poverty in the counties where buyouts are occurring more frequently, and we see a lower household income in those counties as well. And why might this be? Well, the way that these practices typically work is FEMA will fund 75% of your mitigation project, and 25% the household is responsible for upfront. So likely, a lot of households are unable to actually put this cost out for mitigation efforts if they don't have necessarily that money in the bank. But when a large disaster occurs, these households can often be more affected. So the next thing that we're really trying to do is kind of connect these two things. And one thing that we found is specifically when we analyze the claims history from the NFIP, that the average return period for precipitation events occurring for a given claim is 6 years. We typically design infrastructure for a 100-year event. So most of our measures are happening specifically in the insurance world. Most of these claims are being filed with lower severity, higher frequency floods. So how do we use basically the idea that we have independent agents who are making their own decisions? We have a risk factor that is not the same between different households. And we have folks who are causing serious problems for the insurance pool, frequently withdrawing from the system, but also don't really want to be paying for insurance unless you have a risk. So the best way to do this that we're hoping to continue to work on is to use basically agent-based reinforcement learning. So looking at ways in which we have multiple stakeholders interacting, and you have a higher level machine learning algorithm optimizing for trying to keep people from being displaced. And so we're actually piloting these models, specifically using an integrated components of the work that I discussed previously. So some of our future work, we want to specifically look at places where floods become simultaneously probable through teleconnections. So like sometimes we see these occurrences of major flood events like, in Europe, and then you see similar floods in the US. Well, some of these places have teleconnections through specific climate regimes. So mapping those teleconnections can be particularly interesting, especially when we're thinking about this compound clustered derivation for our simulator. We also want to look at integrating storm trajectories conditioned on tropical moisture exports and considering an adaptive planning framework that also considers elements of non-rational behavior, such as myopic decision-making, because a lot of times folks will remember to purchase or protect against a flood measure 1 or 2 years after the occurrence, but maybe not 6 to 10. So those are all things that we are looking forward to in the future. Thank you.
Hey, thank you everybody so much for these wonderful talks. We're going to invite all the speakers and our moderator, Savannah, back up front to have a facilitated discussion along with some audience Q&A.
Great. Thank you all for the really interesting talk. I was very excited to hear about your very diverse research on this topic. So I have a few questions prepared, and then we'll take some audience questions, hopefully at the end. So I want to start with a question about trust building in modeling. So we all know climate research is very important. It's very relevant to all of our lives. We're all feeling the effects of climate change. And in particular, this event talking about urban flooding is, of course, very relevant to the large urban city that we all live in, New York. But we're also, along with this climate effects that are happening, we're also living in a culture of, at least I perceive, increasing distrust in science, scientific modeling, scientific research, and even academia as a whole. A lot of your research involves very complex modeling, lots of multifaceted, multimodal data. So I'm curious how you think about trust building in this research, both with the general public and especially with policymakers who you're hoping to motivate to take action based on your research. Yeah, and maybe we'll start with Fatoumata.
I believe that trust building is extremely important, and it is important to get the community engaged and to have wording that is not super jargony so that individuals are able to understand what actually is going on and what individuals are trying to implement within their area. So I believe that educational material, hopefully like the website that I'm making, will allow individuals to understand different risks that are happening within their areas or different proposals that are being put in place and how it may impact them and what they can do about it.
Thank you. And I'll open it up to the other panelists as well if anyone else wants to comment, maybe Candace or someone else.
Sure. Yeah, I would say in general in academia, and this is historically true, but I have not seen like a great amount of improvement, is there is not a lot of incentive structures for researchers to engage proactively with folks, specifically folks on the ground. And so I think particularly when we think about how these risks are becoming kind of like increasingly exacerbated, we need to really be thinking about the knowledge base and the resources that our communities really provide in a way that doesn't think about things in such an elitist hierarchical way, and starts to consider knowledge and community knowledge as equally valuable. Because especially if you like live in a home that's having repeated flooding, you probably know where that flooding is coming from a little better than someone who has never been there. And that's something that we as modelers sometimes struggle with, because we do want, I mean, our goal is to model everything very precisely, but that doesn't mean that we don't still have a lot to learn.
So in regards to trust, I think researchers should begin to adhere more to the standards of reproducibility. This is providing clear text in the papers, code availability, data availability. I think when other researchers are able to reproduce the results, then that gives it more, that provides for more trust. So I believe that as we're starting to use more computational methods, that we need to focus on making our work more reproducible.
I fully agree with what has been mentioned. Trust is built by engaging the communities in the process of determining the optimal solutions. If academicians work on their own and publish the results of their work in scientific journals, it's not effective. If we want impact, direct impact to our communities, we have to engage the communities throughout the entire process. And this is something that we have to improve. We have to improve in the future, in my opinion.
Yeah, thank you all for those great answers. I totally agree with everything that's been said. I think community engagement is really important. And like Adam said, we haven't always done a very good job of that in academia. But I think there's a lot of opportunities, especially in the climate space, to improve on this. So I'm a physicist originally by training. My PhD is in physics. And for a lot of you, you mentioned that your work involves a large component of physical modeling or physics-driven simulations. I'm curious how you think about validating those kinds of physics-driven models, especially when the kind of systems you're looking at with weather, climate, flooding, have a lot of variability, a lot of stochastic behavior, and they carry large uncertainties, especially when we're trying to project into the future, or they're inherently probabilistic. And maybe yeah, we can start with Adam.
Yeah, this is a super important question. I would say, I think Well, I guess I'll say two things. And the first is like, while machine learning and AI has been so incredibly valuable to our ability to increase precision in our models, it's also become very dangerous just in the ways in which like the last like the black box model often becomes very challenging for interpretability and also less accessible in some ways to communities. And some of the ways in which I think validation is a responsibility for our modeling community is to first, there's a lot of incentive to, be trying the newest model, but fully understanding what you're actually implementing is very important. And secondly, also thinking about ways in which we are baselining our assessment metrics across more standard platforms. I think that is challenging sometimes because, in all honesty, there's an entire community of modelers out here that make models and publish models that are never used. So the important part, I think, is to be realistic about that and be practical, and also like think pragmatically about why are you building this model and what is its intended use. And that also goes back into some of like what Candace was saying with, code availability, being proactive about how your code is being written so it's actually understandable, etc. So, and that also feeds into partnerships.
Yeah. Candace?
I have not built a hydraulic model or a physics-based model. So I can't directly answer your question. Or maybe I don't feel that I should, I guess, because a lot of it will be speculative. I haven't really read up on the research recently on hydraulic models. But yeah, I think there's some skepticism on AI, as you were saying. I think I was reading an article, maybe from Fortune, that was saying that we have to separate maybe machine learning from AI. A lot of times people are thinking of large language models nowadays, but machine learning has shown to be successful in creating predictions. However, it seems that the large language models are going to continue an upward trajectory where they're going to be able to build upon each other. And they're going to be agents based off of agents that could simulate many mental capacities. So I think it's just accepting the reality.
Thank you. George, any thoughts on validating physical models?
This is an extremely challenging problem. What has been done in the past is we were validating models using results from past catastrophic events. The problem is that there are very few major catastrophic events. So the validation and the updating and the improvement of the models were based usually on a large number of relatively smaller events. And the models were working quite nicely. And then a big event was coming in, throwing the model completely out. And then another effort was made to include this big event, and the model was working again. And someone was very happy, saying, okay, now the model works both for small, moderate, and a big event. And then another big event was happening, and the model was not being able to describe it with accuracy. So it's a very difficult problem. It's a classical problem of limited data, and different major events have sometimes very different patterns. The only hope is, I mean, let me take the word hope out. The expectation is that in the future, with more major events happening, we will be able to better validate the model. I hope there are no major events. This is why I retracted hope. But unfortunately, they're going to happen, and probably the models will improve.
Thank you. So another common element of a lot of your research is incorporating some kind of human element, whether it's in the form of like stakeholder feedback, human decision-making behavior, or societal goals like equity. This type of information, at least in my own experience of research, can be very difficult to directly measure or model. And I'm curious how you integrate these factors that may be more qualitative or more difficult to like directly quantitatively measure into more technical quantitative models of climate effects. What are some of the challenges with this work, and why is it so important to do these kind of things? Let's maybe start with Fatoumata.
For me, like I said, I use 311 data within my like entire attribute table. So within that, I would have to download that from the Open Data website and filter out all the 311 complaints from that time period. And that would indicate like to convert it from, because within that, it would also show like a description of the complaint, where the location of the complaint was made. But in order for it to be more visually representative, I just made those into points. So and then individuals can see like by number how many complaints and specific zip code was making. So in order to convert, I guess, a qualitative format into something quantitative, I just I just converted it by number. But I feel like it would be more useful for individuals to directly see, like, because certain complaints, they indicate whether or not there was something found within that, or whether it was just like an empty complaint or not. So if there was a way to indicate the specific like format of the complaint, that would be a better way to map it visually. So that's also something that I can consider in the future.
Thank you. I know, George, you mentioned explicitly like aligning with societal goals like equity in your work. I was wondering if you could talk a little bit about how you integrate that that kind of goal.
We engage communities in our work, and a very, very difficult and controversial issue is strategic retreat. We can identify some communities that we believe in the next 10, 20 years should move to higher ground, because even now they are getting nuisance flooding every year with sea level rise. This is going to increase. Eventually, it will become unsustainable. And let me take a scenario now. A low income community on the coastline. And we tell them, we studied very, very hard, and we determined that your community cannot stay in this location for the long term because of sea level rise and coastal storms. And the community follows our recommendation and relocates to higher grounds. And then a real estate developer comes in and builds luxury condominiums raised, I don't know, 10, 15 feet from the coastline. We will not look as fools. We will be fools in such case. So in my personal opinion, the way to do it is the following. And in my opinion, the only way. Once a specific location, community, is considered one candidate for relocation, there should be legislation that forbids building in this specific location for the next 2-3 centuries. With the exception of if you want to build a park for recreation purposes, that's fine. But building for residential buildings, businesses, and should not be part. This is going to introduce a level of confidence to the community, saying, okay, if there is legislation not allowing anyone to build after we move out, This might mean that indeed this is a case that we should take seriously into consideration.
Yeah. Any other comments on integrating social goals or constraints into models?
Yeah, I can talk a little bit about what we're up to. I guess going off of what Professor Deodatis just mentioned, it's really interesting. We're doing one project right now where we're interviewing a number of stakeholders and using those interviews to inform game theoretic models of the social dynamics. And some of these trade-offs are just very challenging in general because they don't necessarily employ what like mathematically is the like quote unquote best solution. For example, you have a community that needs to move, but you have folks who don't want to move, and then like are still insured because we have a public insurance program, so they can still purchase insurance. Um, that causes a bit of a problem because especially if folks feel that they can continue to either recover their costs or get enough subsidy to continue to stay. I mean, there's also an extremely large social and cultural and psychological value to like your home and your place in which you live. So it doesn't become a sort of uniform trade-off. But there are things that we can do, I think, a little better in the modeling community. For example, a lot of times, a classic example is like taking an expectation over an infinite horizon, which is oftentimes how we want to make decisions, or like if we're looking at a 100-year project, take it over 100 years. Well, if folks are thinking myopically and they're making their decisions financially on a year-to-year basis or on a 5-year basis, we can change that horizon mathematically, and you can get a better sense of like that perspective of how people might be actually thinking about their estimated cost. And a lot of times that isn't necessarily like sound for decision making, but I think it is more important that we shift in that direction when we're simulating individual behaviors, because what we found in the research is that people typically forget about flood induced, like have limited in amnesia after 5 years, which is what they've coined it after an event, and tend to forget about it or not think it's important. So insurance rate uptake drops off. And so there's just different ways to employ this, I think, that could be more pragmatic within the tools that we do already have.
Thank you. We heard a little bit already on the panel and in your presentations about the role of machine learning and AI. I'm curious, yeah, to hear a bit about what you all think the future of the integration of AI and machine learning and climate modeling is. Obviously, that's a big focus for LEAP here, but it's also increasingly a focus in the broader AI and machine learning community, everything from, just building better physics-driven, physics-aligned models to claims that we're going to have artificial general intelligence that will just figure out how to solve climate change for us. So yeah, any thoughts on the future of AI in this space?
So what I'm thinking is that there's already AI where you could write in a request to the LLM. The LLM will code it and then it'll run it on the same platform. So, and eventually the LLMs will be able to consult with each other and they'll be able to make decisions. So, and then you can make an LLM that'll be personally tailored to you. So you'll have your own LLM. So I think AI is going to take a big portion. I think things are going to change. And obviously there's room for human intervention and human research, but I think things will change in the near future, but I do. So I do believe AI is not going to go anywhere.
Any other thoughts on AI?
I guess one thing I'll say is I think I completely agree that it's obviously AI is going to become a huge part of our work and also the ways in which we are able to produce work more efficiently, which I think is really exciting. I think the parts of it that are going to be a challenge, especially for the research community, is going back to, putting some like guardrails up in terms of thinking about first off, like fully understanding what is being implemented, because a lot of times it is easy for an AI model to, an LLM to output you an answer to a question based upon, the crowdsourced responses, but it might not be even remotely close to a good answer. And a lot of that is because it's trained, it's a data-driven approach where we're training these models on just very, very vast amounts of data. And sometimes if there's enough of idea that might be perfectly fine, but maybe not the best idea, you'll get that. And so it's important to know what you're getting out of the system. And then also it's important to think pragmatically about how it can be better, because things like, I think even just using flooding as an example, a common metric for us for, assessing your model on performance is like a mean squared error, for example. Well, if you're looking at the mean squared error and you're looking at all of the daily data for a river, that's not particularly useful for floods, because we actually only care about the 90th percentile and above for the most part. So you need to be pragmatic about how you're actually using that metric. And a lot of times, even in the research, we see a lot of models just being assessed on just that, the daily time series and it's a flood model. And that sort of thing is not particularly useful. So it's good to know, what you're actually using the system for and what's the intended purpose.
Thank you so much. Yeah, thank you for all your responses to these questions. This is really interesting. Do you have time for audience questions? A couple?
Yes, thank you, everybody. We do have time for, we are actually at about time, but we'll take some questions. Anyone on Zoom can put their questions in the chat. And any students here for Dr. Elsa Esser's class can head to the conference room. And everybody else, we have mics available if anybody has questions.
Hi. Okay, excellent. Hi, everyone. I'm Stella. First, I would like to thank all panelists for the amazing presentations. I have worked with flood risk models in my PhD as well, so it's great to see different perspectives on the problem. I wanted to ask about specifically like specific recommendations for transforming these models into action, like because it's flood risk models, we want to transform, like we want to implement these solutions. Now I work in an institute with the same purpose to implement science into action. So what are specific recommendations that you can provide that can help policymakers and implementers to actually use these models to implement? Like George gave some examples, like to use scenarios with price tags on the scenarios, like budgetary limitations. And what are other specific recommendations that we can use to design these models so that they can be actually implemented? Thank you.
I guess I would say a couple of things. I'd say first, it's really important to have a solid partnership for implementation, and people like that does require time. And I think and maybe this isn't the optimistic perspective, but the only ways for potentially from academia to make it more substantive for implementation, what you're doing requires you to, invest a substantial amount of project effort and research funds towards that partnership that is not just going to be, one PhD student. It's going to be a huge portion of your lab. And so if that's the intended goal, that you're going to be working actually in some ways against the metrics that academia rewards you for. So I would say in some ways, the best is to work in the, policy private interface. There's some really wonderful groups that are doing work that is like specifically focused in that area. I do think like academia has a lot of potential to respond in this way and like progress. But I'd say the movement is slow. So, if you want something implementable, it requires a team to work together on implementation, which isn't necessarily what the like academic metrics reward you for. So that would be my answer.
I am more pessimistic. Usually after a major disaster, there is a lot of funding, and I'm not talking only about the United States, but all over the world, to repair the damage and do something to protect from future events. After a period of 2, 3, 4 years, the chances of additional funding materializing are going down dramatically. We have the example of the Netherlands. They acted only after 2 major disasters. So this is not surprising, in my opinion, because either a local government, city government, state, or federal government, when they make the budgets, they have very important priorities. I gave the examples of healthcare, education, and so on, and say, okay, I'm going to take out $10 billion to protect the city from something that might happen 20 years from now or 40 years from now. Is not very high on their agenda. My personal prediction is that this is going to start being seriously thought when sea levels will have risen significantly and or storms having become much more frequent and more intensive. With the current conditions, if you distance yourself 3, 4 years from a major disaster, finding additional funding is going to be very, very difficult. But what academia has to do is have a plan ready. When the conditions worsen a lot, a plan should be ready for implementation.
Thank you. I think we have a question on Zoom, and I see some more in the room as well.
Yes, this is a question from Anna Kramer. How are you thinking about the compound effects of coastal flooding and inland flooding in your work? These are often modeled separately, but as we've seen, these two hazards can often be coupled in one event.
Yeah, that's really important. So in our work, the first simulator we built is specifically for compound riverine events. However, we're also trying to integrate this with storm surge so that we have like a multi-layered effect. So like specifically for coastal areas, and potentially if there's a, tributary flowing into the ocean at that point, it could be riverine and coastal. But generally speaking, I think another factor is like thinking about fluvial or inland induced flooding that has nothing to do with like the coast or the stream. And that in itself is another challenge. So it's interesting to see like how much uncertainty we have in these specific areas because the challenges are numerous. So I wouldn't say there's one clear solution right now, but I think it's of high interest, and I'm sure Professor Deodatis also has some insight here.
I think that's a good question for the physics-based model. For the data-driven technique, if you're looking at flooding as a response variable, then you're looking at
either cause, since flooding really is flooding. And you can look at coastal variables such as sea level rise, and you can also look at some of the inland variables such as percent impervious. So you can look at both of them at the same time. Yeah, so I think I'll just say that if you're looking at data-driven techniques, especially time series, then you're looking at the occurrence of flooding, which is either one of those.
To tag along, I would say, like in the case of mine, like my research I also have like coastal flooding and riverine flooding included within that. And like to also, I feel like topography would be a good use of a tool. So, and then you can understand whether areas are at risk for flooding or not. So it could be more visually representative.
Yes, absolutely. Both have to be taken into account, plus wind-driven damage during a hurricane. And probably it's time for people who have worked in two different aspects of the problem to join forces and work together.
Hi, I'm Giovanni Capini from Italy and from a research center called CMCC. I wanted to ask two questions. One is if you used or exploit citizen science as a way of involving citizens in observing flooding or these extreme events. That's the first question. And the second is in Europe, well, at least there is an attempt of facilitating the access of this model solution. We call it digital twin, in this case of the ocean, and especially moving to the cloud and allowing, let's say, intermediate users to better use or easier use what if scenario that you have shown. So I would like to ask if you are part or if you are, let's say, embracing the same challenge and attempt. Thank you.
So I have yet to use like citizen science, like surveys or anything like that. The only thing that I would include is the 311 data, but I feel like it would be useful to like possibly go around the Bronx or find a way to collect data from individuals specifically to see whether they would say that they experienced flooding. And I would try to find a way. I feel like within that, it would also be good because it would like facilitate a way to inform individuals of the website of informing individuals about the proposal that's being made. So I feel like a challenge that I have is not knowing, like once I make the website, okay, that's good, but what do I do with it? How do I spread it? So possibly like using open science and including other individuals from like the community would assist in facilitating that discussion.
Yeah, I agree. The 3-1 data, it's a crowdsourced data set. And I think what you were saying is a good idea. Maybe encourage the use of it, perhaps have a cloud-based platform. I think it would not be a bad idea to, if there's a upcoming rainstorm, to maybe alert the people in New York or whatever city you're in to use this particular platform. So that way they're more aware of it. And that way we can get real good data and we can see where the flooding is happening. So I don't know if too many people are aware of the platform or they're not aware that there's a street flooding option, but it is nice that New York City has it.
Hi, so thank you for your amazing presentations. I have a question that's a bit more foresighted. So there were there were solutions that were regarding the permeable like materials that might be helping in soaking up the flooded water, and there are many other technologies that are being researched on. So I want to understand that at what stage do we try to analyze the actual implementation of like the scope of implementation of these? So it's not about the policy that I'm talking about. It's like we need to understand how many hours of disruption we'd have and how much resource is going to take and whether it's actually practically possible to implement these. So what would be the right stage to consider data in that form? And we need to create a data set for that in order to be able to create models in turn. So what, according to you, is the best time to do that? Is it now, or is it like after a certain stage? And how would you like to proceed with that?
I can start that off. I think it's hard enough for insurance companies, from my understanding, to model the damages of one asset, let alone a multitude of assets within a certain area. I think it would be nice, but to get an idea of exactly the economic damage, it would be a very good undertaking. I just don't know if it has particularly been done with great accuracy, but that's my opinion.
I think there's like two main questions here that I'll like sub questions that I'll talk to. One is like in terms of like the implementation of some of these like either nature-based solutions or engineered solutions. A lot of my previous work actually was on green infrastructure implementation in Portland, Oregon. And like some of these municipal governments have data sets where they track all of the projects, and then you can model from those data sets and like have citywide efforts for like subsidies for those. So that's like in Portland, there's green infrastructure database. So then you can model that, which I've done previously. At the same time, there's like as a modeler, I'm always asking the question of like, what do we need to know, and like how much precision do we actually need? Because the computational resources for these sorts of things might not actually be that beneficial. Like for example, like what Candace was saying, like if you're trying to model like an entire city with all of the geographies like to a very, very precise level, but yet you could get that same estimation from a like in of estimation of damage from a much simpler model. Why not just use the simpler one? Because it will be less expensive, it will be more user accessible, and it can like allow us to scale things much better. So it's like kind of this that's always the question as the modeler is, right, is like what do you actually need to know from the model, and how do you make your decisions based upon that knowledge? And it's not, I think, like especially with AI, because we and like our computational resources have just scaled so rapidly in the past decade. Like a lot of times the answer is, oh, let's just be more precise. Well, like how much does it add? If you have a really precise model, but it gets it wrong the same amount as, linear regression, why are you running that model? And I think we don't ask that question quite enough.
Thank you. I think we're going to take one more question from Zoom, and then I know there are more questions. We have the room until 2, and the speakers will be around, so please ask your questions to them. Yeah, thank you.
Yay, Zoom has the last question. We have a question from Khalil Megji. I hope I pronounced that somewhat correctly. Forgive me if I didn't. The question is, can you speak a bit more about the economic impacts of climate change, flood, sea level rise, etc.? Are there any resources or data that quantify that economic impact particularly well?
I know it's large, and I know that there are some data sources. I just don't know it off the top of my head, but yeah, there are some pretty interesting data facts in regards to climate change and the financial effects of climate change. I'm sure it's in the. I believe I heard someone talk this week and say it's in the trillions, but I can't specifically comment.
I believe that FEMA's National Risk Index would also indicate whether areas are at risk for certain like storms or what have you, but I'm not sure if it specifically says like the metric at which like a area is like how much loss it would have. I think it does, but like on my map, it might not be visually representative, but within the larger data set that they have of the entire US, it definitely has that within it.
Okay, thank you so much to all of our panelists. Let's give them a round of applause.